A new computationally efficient method for spacing endpoints equally on a sphere. The problem of spacing any number of points equally on a sphere is extremely intriguing because it is impossible to solve. Now I know that you are probably thinking that this seems like a simple problem, but despite seeming simple, it is actually quite challenging. In fact, it is impossible. The easiest way to understand why this problem is impossible to solve is to look at the configurations for small numbers of points. Let's start with 2 points spaced equally on a sphere. It is just 2 points on opposite poles. When it is 3 points, it is the vertices of an equilateral triangle. When it is 4 points, it is the vertices of a tetrahedron. When it is 6 points, it is the vertices of an octahedron. Those are all cases where it is possible to equally space points on a sphere. This problem becomes difficult when one realizes that for certain numbers of points, there is no way to perfectly space the points. For example, when there are 5 points on a sphere, there is a configuration where the points are as equally spaced as possible, but they are not equally spaced because the points have 2 possible distances between them, the square root of 2 and the square root of 3. To add on to this challenge of having some numbers of points that cannot be equally spaced, there are some numbers of points that don't even have configurations that are considered to be optimal. This makes it even more challenging to develop an algorithm that spaces any number of points equally on a sphere. Spacing any number of points on a circle is easy. One just uses polar coordinates and rotates in radians 2 pi over n times. This Mathematica code spaces n points equally on a circle. Unfortunately, the solution for spacing any number of points on a circle cannot be carried over onto the sphere, and the algorithm cannot be modified to work on a sphere. In the past, work has been done on creating algorithms to space any number of points equally on a sphere. The best methods use calculus, and they work by having all of the points repel each other continuously until they reach an optimal configuration. The problem with these methods is that they are extremely slow, and for large numbers of points, they take a long time. What I have created is an accurate algorithm that spaces n points equally on a sphere without using calculus, allowing it to work on large numbers of points efficiently. The first step in creating my algorithm was I used spherical coordinates to program a function that put a spiral around a sphere. I then added a new variable called x, which allowed me to manipulate the broadness of the spiral. As I changed the x, I found that some configurations of the points appeared to be much better than others. At this point, I went out and found many optimal nx pairs. When I closely observed the configurations of points, I realized that there was clumping at the poles. I fixed this by having the spiral stop just before they reached the poles, allowing me to raise the accuracy of the function. After this, I then plotted the pairs, and noticed that they appeared to be part of the linear function. Using this knowledge, I realized that I had to find the linear function that provided an x for every n. I did this by developing a few accuracy functions, and I then used them to find that the optimal x for 200 was 240.1. Seeing that the linear function from before had a slope of around 1, I tried a bunch of different slopes near that for my function. I then continually narrowed it down until I found many different functions that were almost indistinguishable. I then plotted these optimal functions' accuracies. The one that stayed the highest for the longest was the best. This function was 0.1 plus 1.2n. I then put 0.1 plus 1.2n in as the x in the function, and the results were great. As you can see here, the function worked for any number of points quickly. When analyzed, the accuracy of the function ranged from around 70% to 86%, and was incredibly fast even as I got to numbers of points as large as 50,000, which is incredible, seeing that this problem is impossible to solve and this algorithm does not use any calculus. Endpoints equally spaced on a sphere has many applications in the real world. First, it would have been quite helpful in the Starshine 3 student satellite project, in which mirrors had to be spaced around a spherical satellite. The algorithm also can be used to model the handshake problem in 3 dimensions. The handshake problem is, if there are n people in a room and they all shake hands with everybody else, how many handshakes occur? It is usually modeled on a circle like this, showing all of the handshakes that occurred as lines. But with my algorithm, it could be modeled on a sphere as well, making it look that much cooler. In addition to being used in engineering satellites and demonstrating famous math problems, my algorithm can also be used to make beautiful art. Here I used the algorithm recursively and got this breathtaking piece of art. One other thing that I have done with the algorithm is I used it to create a 3D model. In addition to those applications of the algorithm, it has many other applications in many different scientific fields, including multi-electron bubbles in superfluid helium, virus morphology, protein S layers, and coding theory. It can also be applied to problems like structural chemistry, the design of multi-beam laser implosion devices, and the optimum placement of communication satellites, allowing for the world to use the minimum number of satellites to provide service all over the Earth efficiently. That application alone has the power to save millions of dollars that might be spent on unnecessary satellites. The final application that I will speak about is that my work has led to the creation of the new built-in Mathematica function, sphere points, which will be added to the programming language soon. The impact of this is that any user of the programming language will soon be able to type sphere points of n, and they will get any number of points on a sphere to use in whatever way they want. This makes the applications extend to whatever Mathematica users could imagine. Yes, I do believe that the only limit on applications of the algorithm is people's imagination.